Hello students, good time to all. I am Chandan Kumar Pradhan. Welcome to your YouTube channel Chandan Physics. In this video, we are going to discuss another applications of Maxwell's thermodynamic relation as energy equations. Let's begin. At constant temperature, treated as constant, the internal energy of a real gas changes with volume as well as pressure. As we change the volume, then internal energy change. As we change the pressure, ultimately the internal energy also changes for a real gas. Means internal energy is depend upon volume and pressure at constant temperature. Let us derive a general relation for the change of internal energy that is U, or change in internal energy, that is du, using Maxwell's thermodynamic relations for pure substance. Let we assume that the internal energy U, which is a function of temperature and volume. So therefore, the change in internal energy corresponds to change in temperature and change in volume. Therefore, du is equal to del U by del T constant volume dt plus del U del V at constant temperature dV. Let us take as equation number 1. We know according to first law of thermodynamics, dq is equal to du plus pdv, or dq is equal to tds du plus pdv. Now du is equal to TDS minus PdV, where S is the entropy, V is the volume and T is the temperatures. du is equal to TDS minus PdV, or del U by del V at constant temperature. That term will be T del S by del V at constant temperature, means we divide del V here, minus P. Here also we can write del U, this is del U by del V at constant, del U del V at constant temperature is equal to, here I use the Maxwell's relations. From Maxwell's relation, del S by del V at constant temperature is equal to del P by del T at constant volume V. Here I use the Maxwell's relation, that is T del P by del T at constant volume minus P. At equation number 2. That equation is known as fast energy equation. That equation is known as fast energy equation. This is the fast energy equation. Fast energy equation. Again we know that du is equal to Cv dt. Now substituting the value of du in equation number 1, what we get? Substituting the value of du, substituting in equation 1, we get du is equal to the differentiation of u, that is Cv dt, that is Cv dt du by dt at constant volume is Cv. So Cv dt, that is du by dt at constant volume is equal to Cv. du is equal to Cv dt plus del u by del v at constant temperature, del u by del v at constant temperature, that is T del P by del T at constant volume minus P, then dV. To calculate the change in energy associated with a given change of state for a particular substance, the change in energy is calculated here. So integrating on both sides, integrating on both sides, we get this u is equal to integration over Cv dt plus integration over T del P by del T at constant volume minus P dV. This is the internal energy, that is the internal energy associated with a given change of state for a particular substance. Now, using that relation for ideal gas and for Van der Waals gas, then we observe how internal energy is related. That is the equation, that is the equation that is the equation of internal energy associated with a given change of state for a pure substance, Now, for ideal gas, for an ideal gas, what is the observation? Taking 1 mole of ideal gas, taking 1 mole of an ideal gas. So, the gas equation PV is equal to RT, therefore, del P by del T at constant volume is equal to R by V. By taking the temperature to be constant, the first energy equation is written like this. From first energy equation, by taking temperature as constant, then from first energy equation, that is del U by del V at constant temperature, del U by del V at constant temperature is equal to T del P by del T at constant volume minus pressure minus P. So, del P by del T at constant volume is equal to R by V. So, T R by V minus P, that is T R by V minus P, that is P also, that is P minus P is equal to 0. Since we know PV is equal to RT, so TR by V is equal to P RT by V. We get del U by del V at constant temperature is equal to 0. So, that equation written like this, therefore, we write here the internal energy, therefore U is equal to integration from T1 to T2, what is CV dt, that term will be 0, that term will be cancel out, only existence term is CV dt. So, that is CV dt, where T1 and T2 are the initial and final temperatures. T1 is the initial temperature, T2 be the final temperature, or the internal energy U CV integration from T1 to T2 dt, or U is equal to CV, that is T2 minus T1. Look at that of particular equation, that so that the internal energy the internal energy of an ideal gas is independent of volume, is independent of volume when the temperature is constant, when the temperature is constant. That for ideal gas we take how energy is, internal energy is related, that so that the internal energy of an ideal gas is independent of that of volume, independent of that of volume, whereas temperature treated as constant. Now for Van der Waals gas, how internal energy behaves? Again for Van der Waals gas, Van der Waals gas, or we can say that is the real gas. Taking 1 mole of Van der Waals gas, taking 1 mole of Van der Waals gas, or we can say that is the perfect gas or real gas. Real gas, the gas equation is P plus A by V square is equal to RT by V minus B, where A and B are the Van der Waals constant, as we know. P is equal to RT V minus B minus A by B square. Now differentiating it with respect to temperature. Now differentiating with respect to temperature T, we get that is del P by del T at constant volume, that is R divided by V minus B. Now using that relation, first energy equation, from first energy equation, first energy equation, that is del U by del V at constant temperature is equal to T del P by del T at constant volume minus P. So del P by del T at constant volume, that is R divided by V minus B, that is RT divided by V minus B minus P. We get that is A, that term RT divided by V minus B minus P, that term is A divided by V square, A divided by V square, del U by del V at constant temperature value. So the internal energy will be, therefore internal energy U is equal to integration from T1 T2 Cv dt plus again that is T del P by del T at constant volume minus P dV, integration from V1 to V2 A by V square dV. Here du changes from U1 to U2 let. Initial internal energy, that is the final internal energy. That is for internal energy. I write here, that is internal energy. So U2 minus U1 is equal to Cv T2 minus T1 minus A 1 by V2 minus 1 by V1. Look at that equation, how exactly that equation indicates, means the change in internal energy depend upon the temperature and volume, but not that pressure. But in previous one, for ideal gas, that is independent of volume, there will be only the temperature term. So, in case of real gas, what happened? The internal energy of real gas, depends on the volume, that is depends on volume. That indicates with the increase of volume, the change in internal energy also increases, even though the temperature remains constant. How actually that happens? Due to the potential energy of the interaction decreases as there is increase in the intermolecular separation. This is how internal energy is related in case of real gases and in case of ideal gases. Again, to study the dependence of internal energy and pressure, to study the dependence of pressure, the dependence of internal energy on pressure, internal energy on pressure, we assume that internal energy U is a function of temperature and pressure. Therefore, du is equal to del u by del t at constant pressure dt plus del u by del p at constant temperature dp. Now, using the thermodynamic relation as, or let del u by del p at constant temperature, the term del u by del t, in place of del u by del t I can write that is T del S by del P at constant temperature. Okay, just here we know that equation not we know that du is equal to TdS minus PdV, as we derived here. du is equal to TdS minus PdV, like this. du is equal to TdS minus PdV. Therefore, du by del P at constant temperature here, so that is T del S del P at constant temperature minus P del V by del P at constant temperature. Now, from Maxwell's thermodynamic relation, we have that is del U by del P at constant temperature is equal to, that is written as del S by del P from Maxwell's relation, del S by del P at constant temperature is equal to minus del V by del T at constant pressure. that relation put it here. So minus T del V by del T at constant pressure minus P del V by del P at constant temperature. That equation. That equation is known as the second energy equation. That is the second energy equation. Again, putting the value here means du can be written as, putting the value of del U by del P at constant temperature to that side, that will be du is equal to that much. That value is again put it here. So with the help of this video lecture, we understand the derivation of energy equations from Maxwell's thermodynamic relations. That is the one of the application of Maxwell's thermodynamic relations. We derive energy equations. This is the first energy equations, and by using that energy equation, we relate how internal energy is related to ideal gas and Van der Waals gas. For ideal gas, we take, for ideal gas, the internal energy is independent of volume when the temperature is constant. Then for Van der Waals gas, it is so that the internal energy of real gas or Van der Waals gas that depend upon the volume. And finally, taking the relation as the second energy equation, del V by del P at constant temperature is equal to minus T del V by del T constant pressure minus P del V by del P at constant temperature. So with this useful and informative notes, let me wind up this session. Thank you.